So now what we're going to do is we're going to solve the general differential equation where you've got the rate of change of a quantity is directly proportional to the amount present. And we're going to see that this will always result in an exponential function. So here's dy dt equals ky. So when we separate the variables, we get that dy 1 over y times dy is equal to k dt. And taking antiderivatives as usual, we get the natural log of the absolute value of y is equal to kt plus c. Using the definition of log, we get that absolute value of y is equal to e to the kt e to the kt plus c, which is e to the kt times e to the c, which we're going to write as just a. So that means absolute value of y is equal to a e to the kt. Again, I'm just going through this quickly because we did it in the last example. And then again, that absolute value, since we don't have an initial condition, we can just let the a determine the plus or minus of that. And so there is our solution to that differential equation. Some books write it as y equals, like they'll say with y sub 0 or something, like the initial amount present. So I mean, I used a, I guess it doesn't really matter, but sometimes they use the same variable as the the dependent variable, just with a subscript. But in any case, the result here is what's called a law of exponential change. So what that says is that if dy dt is equal to k times y, and again in words, this just means that y changes at a rate proportional to the amount present. Right? Then that means that, and let's say y equals, I guess we'll use the subscript version. If y equals y naught, when t equals 0, then y equals y sub 0 e to the kt is the solution. And we've got a couple situations. If k is bigger than 0, we'll look back up to the differential equation, dy dt equals ky. If k is bigger than 0, then that means that the rate of change, and I mean y is the amount present, that will almost always be a positive value, then dy dt equals a positive number, and thinking of dy dt again as slope, you're dealing with a function whose derivative is always positive, or slope is always positive, which means that when k is 0, it's exponential growth as opposed to decay. So this means exponential growth. Exponential. And if k is less than 0, well then your dy dt is going to equal a negative value, and that means that it's going to be exponential decay. So what we're really doing is we're kind of just rederiving things that you saw already in probably prior math courses, but we're actually deriving them from the differential equation. And so the thing to focus on, and what will happen is you probably won't be resolving these all the time using separation of variables, because you should recognize the structure of the differential equation and know that it's going to result in an exponential. But you always could if you forgot. I mean, this wasn't too painful of a process. But the point is, the solution to that differential equation is always going to be an exponential. All right, and so you can start from that observation and work your way up to the functions and equations you've been using all along in your high school math career.